There's a warehouse in France, right on the Swiss border, where the most expensive material in the world is created. So Wikipedia seems confident, but I'm not so sure we can even call it material, because it's not made of regular matter. This stuff is the rarest and potentially the most dangerous on Earth. And scientists from around the world are just trying to figure out how to put it in a bottle and carry it across the street. Antimatter. But what is antimatter and why is there so little of it? It's the rarest substance on Earth. It's the rarest substance in the universe. But scientists theorize that the Big Bang should have created a universe with equal amounts of matter and antimatter. And yet we look around and see almost completely matter. Why? That is surprisingly one of the biggest unanswered questions in physics, and we're gonna dive into it. Hey, I'm Diana and you're watching Physics Girl. I am back in the United States, but I recently traveled to Switzerland, initially to speak at EPFL in Lausanne, but I decided to stop by the most impressive scientific facility on Earth. So we're in Geneva, Switzerland right now. Oh no, I'm going! We're in Geneva, Switzerland. This is the home of the United Nations. We're headed to the Large Hadron Collider, and I've never been, and I'm really excited. Ah! Okay, so what is this room?
This is sort of the storage locker area.
I'm like, wow,
Storage lockers. So only people with access, special access, can enter here. So this is what they call the AD hall, after the antiproton decelerator, the AD.
Yeah.
Yes. And so this decelerator is beneath us, beneath these concrete blocks. You see these yellow fences?
Yeah.
So that's the big ring going around.
So the whole purpose of the AD hall is to house this ring inside of a concrete tunnel that slows down antimatter particles, and then subsequently there are experiments that study it.
We're doing the opposite of the rest of CERN.
Yeah.
We don't like protons, we want the antiproton. We don't like accelerating, we want to decelerate.
It's all shut down right now for maintenance, so we got to go down in the tunnel.
Whoa.
Wow, there's all this concrete and cement. Oh my gosh. I just went to Burning Man. I feel like a lot of people were wearing this stuff.
So the blue things, they are bending magnets. So they're typically at the corners of your ring, and they will turn your beam, you know, give it a kick or a turn.
Yeah.
The red ones are the quadrupole magnets,
Okay.
and they are used to focus the beam.
It's like Legos, but instead, like each piece in the ring is a giant electromagnet. It's not a coincidence that the antimatter factory is at CERN. You need these super energetic particles driven by the massive particle accelerators at CERN to create antimatter.
Well, the way they are generated, you have these, you know, collisions, big amount of energy, and from this you automatically have a side product being antiprotons that are created.
They need to direct the antiprotons toward the AD hall using these giant coils of wire.
It's connected to some transformers, which will send this current to the magnet, so you can have this tiny kick of your beam path.
So all that specialized equipment and the crazy amounts of energy you use to create energetic particles is part of why antimatter is so expensive. In 2006, antimatter costs an estimated $25 billion per gram to make. Sounds like a lot, but that's just for positrons. For antiprotons, some estimates put the cost at about $3 quadrillion per gram. To figure out why antimatter is so rare, we have to first look at why it can be so dangerous. When antimatter comes into contact with regular matter, they annihilate. They disappear and they turn into pure light energy. If 1 teaspoon of antimatter came into contact with regular matter, it would create an explosion large enough to destroy all of Manhattan. For comparison, you'd need about 200,000 metric tons of TNT to release the same amount of energy, or 10 nuclear bombs. To make it even more relatable, the amount of antimatter you would need to destroy the moon would be equivalent to the same mass of all the fish on Earth. But let's be clear, the small amount of antimatter that we're capable of making with current technologies is in no way dangerous. So What is antimatter? What is this stuff that's capable of annihilating with regular matter? This stuff would look just like regular matter if we had enough of it to be able to see it. Amazingly, scientists predicted that antimatter should exist before they discovered it, which is gonna help us figure out what it is. This is what happened. You know when you're solving the quadratic equation, x equals negative b plus or minus square root blah blah blah, that plus or minus can give you two possible solutions, but sometimes you get a negative solution and you're like, that doesn't make sense, I'm gonna throw it out. Well, in 1928, English physicist Paul Dirac was working on a mathematical equation describing electron behavior, as you do, and it ended up with two solutions. Instead of throwing out the positive solution, he eventually thought, what if this second solution described something real? It would be exactly like an electron, all the same properties, but with a positive charge. That would be crazy, but he predicted this particle could exist, according to the math.
Already in 1932, in one of their cloud chambers, you know these tracks, they saw an electron with, let's say, the wrong charge.
How insane is physics? They discovered a new type of particle because it just popped out of the math. American physicist Carl Anderson detected this opposite electron and then published a paper calling it a positron, and the name stuck, which makes me wish that electrons were called negatrons. That'd be cool. Now we're in for a treat because unlike many experiments of the time, there's actually a photograph of the original positron passing through a cloud chamber experiment in 1932. This line shows the path of the particle. This was the first discovery of antimatter.
Each matter particle has a brother or sister, and it has the same mass, but it has the opposite charge and the opposite magnetic moment. At least that's what our theories tell us.
So that's what antimatter is, but it's kind of a boring description of antimatter because it ignores the annihilation and stuff. Okay, so 1932, we've had the first detection of antimatter, the same year as the Quidditch match between the Appleby Arrows and the Vratza Vultures. It wasn't until 1995 that physicists made the first atom of antihydrogen. Why did it take so long? Well, annihilation. It's really hard to work with material that you can never hold in your hand. It can't even touch your equipment, or poof! It can't even touch the air, or poof! So this factory in Europe, its goal is to keep making and studying a material worth nearly trillions per ounce. What are they studying? Well, there's one big question keeping scientists interested. Scientists don't know why antimatter is so rare. That's one of the big unanswered questions in physics of our time. So the CERN experiments are looking to study the properties of antimatter and see if they can find any differences between it and regular matter. A few experiments are studying what will happen when you drop antimatter. Will it go down like regular matter? Nearly every physicist says yes, we suspect it will go down when you drop it. But we've never done that experiment. Another experiment is just trying to store antimatter in a container and carry it across the street.
So this experiment is called PUMA. They want to bring this, their bottle of antimatter to a facility across the street. And so there they have different elements that are radioactive. And so if you have antimatter interacting with this, you will get annihilations, but the properties of what comes out of this annihilation will tell you something about how the neutrons and protons were distributed in these nuclei.
And several other experimental groups hope to study the spectral lines of antihydrogen and compare them to hydrogen.
And so we know exactly what colors hydrogen emits. But so we recently were able to do the same type of spectroscopy, looking at the light that comes out of antihydrogen.
And some experiments, like the one ELISA works on, are measuring the properties of antiprotons that they've trapped to see whether they're the same as proton properties.
Base is purely antiprotons, so we typically have a reservoir of antiprotons, about, let's say, 200 antiprotons that we can store in this panning trap that you've seen. And we can keep this, the record was 400 years.
400 years!
400 years, 400 days. And so we take one antiproton at the time, put this in our measurement trap, and we try to measure its properties, so charge, mass, and magnetic moment.
So that's the answer to our question. Why is there so little antimatter in the universe? We don't know yet. That's why all these really, really smart people are doing crazy experiments trying to figure it out at CERN. And I'm really excited to follow along and see what they find, because I know they'll find something. Thank you guys so much for watching this video, and happy anti-physicsing.
You're the messiest boss I've ever had.
I'm not messy. Nothing to see here. Because we have an announcement, which is that we're starting a Patreon. These trucks. So if you were like, oh, what is going on? What's this Patreon thing? It's ostensibly a platform that allows independent creators to be supported through their audience, but it's also an excellent place for a community, and that's what I want. That's why my first perk I decided on was an online hangout with patrons. And then there's signed postcards with experiments on them. Oh, we've been saving up the bloopers. Make a coin. Make a coin. So what next? What are we gonna do with the support from Patreon? Well, I really wanna do bigger projects. On-location shoots like this one at CERN, a Women in Science series done the right way where women just talk about their science, and upgrading equipment. Plus, supporting this really significant recent change to Physics Girl. I have some paid full-time friends. Levi, full-time shooter editor, Heather, mostly full-time producer. And so that your patronage can help keep them off the streets and give me some real friends. No, but really, they...
Well said.
If you want to contribute to the Patreon, my favorite option is just Google Physics Girl Patreon. Oh yeah, you don't have to contribute. If you don't want to, or you can't, that is totally fine. I'm super thankful for just having you watching the videos and getting excited with me about science, because that's kind of the whole point. Yeah. Stop, don't you?